Okay, simple harmonic motion, unit 9. We've got a small mass of M1 rests on, but is not attached to, a large mass of M2 that slides on its base without friction. Maximum frictional force between M1 and M2 is F. The spring constant is K, and it's attached to M2 and the wall. And we want to look at the horizontal acceleration that M2 may have without causing M1 to slip. So we're looking at maxing out that frictional force. Determine the amplitude A for the simple harmonic motions if the two masses move together so there's no slipping. C, the two mass combination is then pulled to the right with the maximum amplitude A that you find in part B and released. And we want to look at the frictional force on the mass of M1 during the first half cycle of oscillation. And the two mass combination then is pulled to the right, A prime, which is greater than A and released. So we have to look at the acceleration of M1 when the instant the masses are released and M2 when it's released. So this is a hefty problem. Okay, let's take a look here. All right, so when we look in part A, having a no-slip condition means that the acceleration of mass 1 and mass 2 are going to be exactly the same. So we then know from Newton's second law that the acceleration of block 1 is going to equal that maximum frictional force divided by M1, and also the acceleration of mass 2 then also has to equal that same F over M1. Okay, for part B, we look at Hooke's law, okay, where we're looking at the maximum amplitude, we're looking at mass, and the mass is the combined mass, and we know that X is equal to A for that X part, and then that X with the dots above, the X prime, is really the acceleration, and that we know is F over M1. So now we can plug in and solve for our amplitude, okay, and we see that it's the sum of the masses divided by K times the acceleration. You need to have some discussion that the frictional force is going to be sinusoidal because it's going to max out its acceleration at the endpoint and it's going to decrease and then it's going to increase again, and so you get that periodic motion. Okay, for part D, we know that when you hit that max frictional force, that's where your slippage is going to start and it's going to end. So that's got to be the maximum acceleration that M1 can undergo. So that stays the same as part A. Then for part for the M2, you're going to have the force of the spring minus that frictional force is going to then equal your M2 times its acceleration, which allows you then to solve for the acceleration of M2. And remember then the force of the spring is going to equal the spring constant times A prime, which is, you can say it as A prime or A plus A prime, and they allowed for the interpretation to go either way. So the concepts of the problem seem complicated, but really try to remember with simple harmonic motion that it's simple. Okay?